We're discussing further material on data types. Probably the most important data type in the language is int. So int gives us a basic way of manipulating integer data, and that data type includes variations on it, and they will be explained shortly. There is a short form, a long form, and an unsigned form. So let me give you my understanding of how to approach learning a difficult subject like programming. In programming, you have lots and lots of stuff. Much of it is obscure. But if you concentrate on the things that are typical, and int is typical as a data type, then you can get 90% of the value of your study or your work by only looking at 10% of the entire language. So this is one of the places where the 90-10 rule shows up. Really make an effort to understand the data type int, and that will help you with all the other and more complicated data types, such as the floating types. On your typical modern machine, an int is stored in 32 bits. That's 32 zeros and ones. And it's even worthwhile, especially if you're going to go into computer science, to learn how to work in binary. That's the base 2, as opposed to how we're writing most things, which are base 10. It's also worthwhile to learn how to write an octal, which is base 8, and hexadecimal, which is base 16. And we may show some of this later on. Now, when you're working with an int stored in 32 bits, then what you can represent is limited, and it's limited to plus or minus 2 billion, and I've written it out here explicitly. You can go positively up to 2,147,436,647, and your smallest number, your largest negative number, another way to put it, is 2,147,483,648. It's not symmetric because of the fancy way people represent integers on the machine. It's called a 2's complement representation. Typically, the first bit is in fact the bit that affects how you interpret the sign. So you also have these other forms of ints: short, long, and unsigned. Short, it means use less data. Long means use more, a bigger range. So short can mean a smaller range. Typically, you're using fewer bytes. You'll see in a second when I write an example that for my machine, short is 2 bytes, ordinary int is 4 bytes, as we've already said, and then long will be 8 bytes. And then there's a further type, which is called unsigned. And in unsigned, you want the data to only be interpreted as positive. So in effect, if you have 4 bytes and you only interpret it as positive, you now have a range from 0 to a little more than 4 billion. So again, this can be very helpful, and it also can mean in a domain where you don't need negative integers, you have an ability to use the machine to work only with that type. Now, for each of these types, there's a way to present a constant. And I'm just showing you here, here's 35, that's an ordinary int. Here's 35 long, and it also can be a lowercase l. This is 35 unsigned, which can also be a lowercase u or an uppercase u, and this is 35 unsigned long. So you should have all of these available on your machine. This is quite important to know which type you're using, both for input and output, because in input and output, the different types take different formats. And you may find yourself mixing the types, and if you mix the types, you have to know what domain you're in, and you have to know how the operations affect values taken from that domain. So a classic problem in programming with a language like C is the fact that the operator divide can be either an integer operator or a floating point operator. And if you have two integers, it's 2 divided by 3, which is 0. There's no remainder. If it was 2.0 divided by 3, or 2.0 divided by 3.0, or 2 divided by 3.0, where one of the arguments or both the arguments are double, then indeed you would be in the floating point type. You would have a type of float or double, and your result would be 0.666. So this mistake gets made often when you are thinking you want to do something like average over some integer data, and you forget that dividing can be either an integer operation or a floating point operation. You can get a mistake. Okay, let's look at some code. So here's some code that I wrote to illustrate some of these ideas. And you can play with code like this. You should play with code like this if these ideas are novel to you. And you should extend it. And you can see in this code, I have a short. Short's a keyword. It really means short int. I could say short int, by just saying short. I'm typing less. So here's my variable name, and I assign it a 5. Here's a normal integer, int normal a, and I've assigned it 67. Here's an unsigned integer, and I use in that literal 67 to have a u. This is a long, and again, in order to make sure that the literal is in the right domain, I say 67L. And then here I'm doing some things to show you what the effects of using that. So here's that divide by 2 problem, where at first I divide by integer 2, and then I'll divide by floating point 2, and you'll see a difference show up. You'll also see that here, for short, I use the format HD, whereas in normally I could have just used D. And here's another weird place where you'll see that the use of the format type will affect how something is represented. So 67, which is the value of normal A, when presented with the format type C, should show up as some kind of character. We'll see it in the ASCII table. And here is where we can print on my machine, because this is a dynamic operation where size of looks up the type and says a short A, which is type short, what size is being stored in on this machine under the system. And we'll see those values as well. Let me run that. And there we are. Short A was 5, divide by integer 2, and we get not 2.5, but 2. But short A divided by the float 2, that should be 2.0, will be 2.5. 67 as interpreted as a character from the ASCII table would be a capital C. And then sizes in the bytes on my machines are 244. The second 4 is for unsigned, and then the biggest is long, which all makes sense. The next data type we're going to talk about are the floating point numbers. As you can see with the little sea turtle, he's really happy when he's floating in the sea. So here are the float types in C. Float, double, and long double. And these are three types that are usually ordered in shortest to longest. And we'll see there is a catch here that's not guaranteed. So the shortest is float, and its range is typically from 10 to the minus 38, a pretty small number, to 10 to the positive 38, pretty large number. For example, scientists think that the universe is something like 10 to the 88th atoms. So that's an even larger number, but this is still pretty significant. For example, on Earth, there's something like 7 times 10 to the 9th people, or 7 billion people. And then that can be expressed with 6 significant figures, as in 0.123456, and then there's an exponent part, which is 10 to the 12th. And showing the exponent part of the float, we use an E. So this is a general way to write the integer part, the fractional part, the exponent, and then a plus or minus integer here. And you can consider that there's a sign of the entire floating point number, a fraction, and the exponent. Now, if we go to, on most machines, a longer type, and typically, again, if you use the size of operator on a float, you'd find mostly that it was 4 bytes, and double you'd find is twice as large, or 8 bytes. And that lets us express more stuff. So one of the things that gets increased is the range. The range becomes from this extremely small number, 10 to the minus 308th, up to a very large number, 10 to the 308th. Then we would have no problem representing the number of atoms in the universe. And we, instead of 6 or 7 significant figures, we typically get 15 significant figures. Finally, we have long double. And long double, when it's implemented and is larger than double, stays with the same exponent range, but it adds a great deal more significant figures. So there's an IBM implementation where there are 31 significant digits. But again, this can be system dependent. So we have, in the C system, these 3 types: float, double, long double. You can declare a variable of any one of these types. The notion is float conserves the most space. Double is typical, so frequently I just use double for most of my things. And long double gets you all this extra significant figure. But the only thing guaranteed by the C compiler is if there's a double, it will be at least as large as float. and at least as significant. And if there's a long double, it will be at least as large as double and as significant. So it could conceivably, on some especially early C system, all three of these could really mean the same thing. But then on some modern supercomputer, they may also be clearly distinguished in the way we just talked about. Finally, we have to know how to write literals or constants. And here's three ways to write the constant 1. Notice 1 is not that way, so it's not possible. If you write down 1 without a decimal point, that's going to be the integer literal. And we're going to see later, when mixing types, this can be very important. So if we want, we can write 1.0, which is quite clear, or 1 point and not have the fractional part, or we could write 0.1 e of 1, which is another way of saying that's a power of 10, so that would just shift it to 1. And this would be the least confusing, but all of these would lead to the same literal as a float. Now, it's important to understand that significance is critical in a computation. So when you're dealing with these numbers, they are not like real numbers from mathematics. In the world of mathematics, there ostensibly is a place on the real line where you could show pi in all its glory, 3.14159, etc., 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 with as much precision as you want. In a standard representation like a double for pi, you could only get your 6 or 15 significant digits represented as a double. So you're going to lose some precision. And think about where this could show up. You might have a computation which looks okay, like you've added a tenth, the real number a tenth, to the real number 1, 2, 3. By real number I mean double. 123 raised to the 10th to the 12th power. It turns out this number is so large that when that's added in, the result is no change on this number. It's dwarfed by the larger part of the number. So that means this computation, if you put it in some expression, would not have an effect. And in more advanced courses on numerical analysis, people who are specialists in this have to keep track of precision, loss of precision, and some of the precision that may come about because a number that looks like it's precise in decimal might not translate to it being precise under the kind of binary representation that's used for a floating point number. So something like 1 1/3, 1.33333, might not have the same kind of precision when it's translated to the internal number. Okay, finally, we also want to know how to do input and output with these floats. So that means we want to know about conversion characters. And we have a selection of conversion characters available. We can use percent lowercase e or percent uppercase e, and then it prints as a number with a fraction and an exponent part. Or we can have a percent f and it prints as a number written out but without the exponent. Finally, we can have a more flexible format, which is %G or percent uppercase G, and they pick from E or F and decide on which one to use based on what gives you the shortest representation. So this is more flexible, but you might end up with one or the other, depending on which is shortest on printing to the screen. Okay, in the next segment, I'm going to use some of those ideas and actually write a little piece of code to show some of those ideas and get you used to printing doubles and also to using the math library, which has functions like square root and sine. So you might look online to do a little work on how the math library can be used. We're going to continue with understanding how to write expressions that change the flow of control. So we're going to continue to use the if-else logic, but we're going to change the kind of expression we test for. And the kind of expression we will test for is a logical AND expression. So you'll see in the heading here, this program is about logical operators and, to understand them properly, short circuit evaluation. This is a program that's going to tell us whether to take an umbrella when we go outside or not. So first off, we have to know whether we're outside. We don't need an umbrella on the inside, and we have to know weather, and we're just going to use very simple values for whether we're inside or outside. Outside is going to be assigned 1 if we're outside, 0 if we're inside. Weather is going to be assigned 1 if it's raining, and 0 if it's not raining. So in the program, we're asking the user, tell us whether you're inside or outside. Enter if outside 1, 1 representing true, 0 representing false. So recall, in an expression in which you test for, in effect, true or false, what you're really testing for is 0 and non-zero. So 0 represents false, 1 represents true. And the same is going to be the case for the variable weather. So here we ask for the weather. And then depending on whether we're outside and whether it's raining, we're going to write, please use an umbrella or dress normally. Well, if you recall anything about elementary logic, the only time a logical AND statement is true, where there are two clauses, A and B, is when both clauses are true. So outside has to be true, namely 1. Weather has to be 1, namely rain. And only then would you printf, please use an umbrella. The other 3 cases all involve dress normally. So you should try to review that or make sense out of that if you're not familiar with that. Now, we're going to talk about a very interesting efficiency hack in the C programming language, which is, in this expression, if outside is false, namely 0, then it doesn't matter what weather is. We're going to dress normally. So when outside is false, the expression is already false. So that means the else, dress normally, will be printed. That's called short circuit evaluation. Imagine that these two things are very complicated expressions. Then they actually would save you a lot of computation. Again, this is the idea behind short circuit evaluation. You needn't evaluate this part of the expression if the first part of the expression already determines the result. I want to look at some detail. And the detail is how to evaluate A and B. And this is just a review, hopefully. And in logic, there are 4 cases. The A can be true, the B can be true, the A can be true, the B can be false, the A can be false, the B can be true. This is what's called a truth table. And finally, both arguments are false. The result true, false, false, false. And again, if you recall, on short circuit evaluation, anytime the first argument determines the overall result, in this case, when the first argument evaluates the false, we needn't evaluate the second argument. So we avoid evaluating the second argument. That's called short circuit evaluation. One last thing about this operator is its precedence very low. And I'm going to go over the whole precedence table, but by very low, I mean it's below any kind of mathematical expression. So if there's a mathematical expression involved in these arguments, then they would be evaluated before the logical and get evaluated. Okay, we're going to have our first example of a nonlinear program. So far, the programs we've been writing and executing are do the first line, then do the second line, then do the third line, keep going until you do a return of 0, and you end the program. Not all programs can be that simple, so it's very useful to have the ability to test something and then decide whether to do one of a number of things. A simple one would be one of 2 alternatives, and that's what we're going to study right now. And later we'll also study how to do things that are looping as well. But this is fundamental. We're going to either do action 1 or action 2, but not both. So this is our first program to use an if statement. So looking at the program, we have what's an if-else statement at the heart of what we're doing. And the program is very simple. It asks the user for a speed. It asks you to enter your speed as an integer. And then, depending on what it sees as your speed, it executes that and says you have no speeding ticket or a speeding ticket. And I think I've already compiled this. Let's just make sure. So it says enter your speed as an integer down at the bottom, and let's say my speed is 78. Sure enough, I get a speeding ticket. Now let me do that again. It says enter my speed as an integer. I say 62, and it says no speeding ticket. Okay. let's go into more detail on the qualities you get in using how to properly use this kind of if-else expression. So the program, which I just called the file is C4E week 3 P1 dash if. And we can see how to use an if-else. The critical thing is the general syntax for it is if expression in between parentheses, then you do what I will call the true statement, else you'll do what I call the false statement. And these expressions can be arbitrary, but they're frequently what we'll call relational. So the expression gets evaluated, and if it sees a value of 0, it thinks false, and if it sees a value that's non-zero, it thinks true. And in the program we just wrote, the relation was speed less than 65. And for example, if you had entered for the speed 50, then that would be less than 65, then that was true, which means that that expression evaluates to 1, which means that the printf is going to print new line, no speeding ticket. Similarly, if you had a speed, again, this relation, speed less than 65, where you entered exactly 65 or more, then this would not be true. That means the expression would evaluate to 0. That means the false alternative would be taken. That means you would get your speeding ticket. Now this could be altered. What if you made a mistake and you said, no, exactly at 65, you're not speeding. And you see in California a lot of highways have a 65 maximum. So if you speed at less than or equal to 65, so this is a different relation. It includes 65, and then 65 remains true. The relational operators are 4 of them. Less than, greater than, less than or equal, greater than or equal. And you should be used to them from high school math. It's also important to know their precedence. Their precedence comes out below arithmetic operators. So operators like plus and times and modulo bind more strongly than the relational operators. So that if you saw speed less than 65 plus I, the sub-expression 65 plus I would go first. That would be done. That addition would be done. It would be as if you had parenthesized this. You don't need to, but you have to understand what precedence is. It's probably a little clearer to do the parenthesization, but that means this plus is done first, so you'd add an I, then you would do speed. So I might be some increment where the highway police gives you leeway. And so maybe typically in your neighborhood that's 4 more miles. So that kind of increment might be more realistic about when you got a speeding ticket. All right, so the very elementary program, you should get out of it how to use an if-else. By the way, a simpler kind of statement is just an if. And in the if statement, you have if expression, and then you execute the statement if it's true. So if you have an expression that evaluates 0, then you omit the statement. And indeed, you could have turned that if-else into 2 if statements, but that would be not as elegant and also somewhat inefficient because you would be evaluating the relation speed less than 65 twice. So in this topic, we're going to deal with iteration. Iteration is critical to computation being useful. If everything was simple and a few lines of direction where we could finish them one step at a time, we largely wouldn't need computers. The reason computers are so powerful is they can do trillions or millions of trillions of operations in a relatively short time, which is impossible for humans or even humans aided with mechanical calculators to do. So this is a true critical topic, and if you master this topic, you have an enormous amount of the utility of writing code and programming. And here we're going to study the while statement. The while statement is fundamental. It's the simplest form of iteration statement. We're going to see in a little bit a more sophisticated form, which will be the for statement. But it's best to understand the while statement. That'll make it very easy to understand the for statement as well. So the while is syntactically while paren with some expression, close paren with some statement. And most normally that statement is what's called a block or compound statement. Namely, it's really a statement that is an open brace and a closed brace with a bunch of statements in between. So you can do more than one statement action. That makes it very useful. Here are the semantics. What we do is we check first to see if the expression is zero. If the expression is zero, the statement is not done. It's omitted, and we just skip to whatever is next. We can think of that as false, though really in C, false is zero and true is non-zero. However, if the expression is non-zero, then we execute the statement that's sitting under the while, and then we repeat. We go back and ask, is the expression zero? We continue. And that just keeps going until we see the expression is zero. Here's an example. While I less than 10, so that kind of expression is relational expression. So that's is frequently what we'll see as a test. And also, this is idiomatic in the sense that very frequently in an iteration you do something that is involved counting, and counting normally uses integer variables. So in this case, I is assumed to have been declared as an int of some value, typically less than 10, otherwise this wouldn't be executed. And we'll check. If I is less than 10, then we continue into this compound or block statement. We do the printf, I equals, and we print out the current value of I. And then, again, very common in iterative statements is we see an auto increment of I. So here's auto increment of I. We add 1 to it. Why? Because we want repeated behavior, but ultimately we want to exit the loop. So let's say I starts at 0. We will print 0, and then we will print 1, then we will print 2, and so forth, until I hits 10, and then we will stop. So this is canonically a very simple loop, but it still has many of the characteristics of even the most sophisticated loop has. There's something where there might be a counting variable. There's some action. This may be actually a whole series of actions, a series of calculations. And this just goes on and on until we exit this loop. In the old days, we used to exhibit this behavior what we called a flow chart. So here's a flow chart for this while loop. We have a test. The test is false. This is the false part. Let me indicate that. So false again, keep in mind false is 0. and otherwise non-false, we execute. Non-zero. So the statement, often a compound statement, and then we go back from here and retest whatever this test expression is. In that case, it was I less than 10 in that example. So we enter the loop, that's the while statement, we do a test, we either exit when false or we continue and do some execution, and then we loop, test, exit maybe, if not exit, repeat, and keep going. If we avoid exiting, we get into what is called an infinite loop, and that's something that you would have to make sure you don't want. It eats up computer time, and generally speaking, it means you've created an error in your program. Okay, we've completed explaining some of the critical details of this code, but now let's see the code in detail and make sure it works. So we're going to create a variable for each kind of item, each character we're trying to count, blanks, digits, letters, others. Since we don't have a count yet, all of them will be initialized to 0. And then we're going to use C to indicate the integer value of the character. And remember, characters are ordinary C are somewhere between 0 and 127, and that's the standard ASCII character table, which you should get familiar with if you haven't until now. And this is a very convenient thing we're going to find from the standard library. We can find it in standard I/O, and that is the getChar function. No arguments, and what it does is it obtains from standard input, which is in this case going to end up being a file because we're going to redirect, but it could also be a typing from the keyboard if we don't do redirection. And here we test to see if we're at the end of file, and this is C, meaning end of file, and that's a constant. It's typically -1, but it's a previously defined constant, which is a special value that would otherwise not be in the file. So -1 is outside the range of the ASCII characters. And we're just continuing that iteration, that loop, until we hit the end of file. Here we see a complex if-else-if statement inside the while loop. Notice I've made the while loop a compound statement, but that was unnecessary. It's just stylistically nice, even though this is actually a single if-else statement, so it was unnecessary. Here's if C equal blanks, then we auto increment blanks. If it isn't a blank, we test to see if it's the integers between 0 and 9. Those are, and that range is strictly, if you go to the ASCII table, strictly those values. And here is a more complicated expression. I'll talk a little bit about it. It's the lowercase letters, but somewhere else are the uppercase letters. So we couldn't just say if C, lowercase a up to Z, so there'd be a lot of stuff in between. But these are all contiguous. Again, the only way you know that is by looking at it in the ASCII table. So this is one range, And also, you'll notice that the double ampersand is logical and that takes precedence over the double single bar, which is the logical or. So this sub-expression gets done first. If that's true, then this doesn't get done. Again, the way these expressions work, this is what's called short circuit evaluation. You could look that up if you don't remember an explanation. It just means we only need to test this if it's true. Then an or expression will always be true. If this fails, then we have to test the second part. And similarly, short circuit works with the and parts. If this part is false, then this little part is false, then it fails for the entire expression. That's called short circuit, so we don't have to do the extra work. And we have blanks, incremented, digits, incremented, letters, incremented, others. And you can do something even more elaborate if you had some interest in developing this program further. And then here we just print out their values. So I'm going to run this program. As I showed in the previous segment, I'm going to use redirection, and I'm going to run it on a file, which indeed is the program you saw at the beginning. And that program had 196 blanks, 17 digits, 302 letters, and otherwise had 152 other things sitting in as characters, which could include things like new lines and tabs. So they could be non-printable characters as well as printable characters. We're going to do more with the while loop because it's so central to iteration. And we're going to show a simple program in this segment, and then we're going to go on to show more complicated programs in the next segment, and then we will do a bit of a quiz. So in the following program, I'm going to write an iteration that's going to ask a question. This is what I call my Valentine's Day program. So put your loved one in front of the screen, and then start your executable, and it'll ask you how much you love that person. And then depending on a score, what you input, it will print out your Valentine's message. So you can see that I just want to emphasize, and that's where repetition is going to come in. I'm going to emphasize how much I love you. And this program is dedicated to my wife. So let's look at some critical parts of the program. First off, there's going to be this declaration for the integer repeat, and that's going to tell us how often the loop is to be repeated. Now, the while loop is the fundamental loop. It's the simplest form of loop in the C language. Later, we're going to see a more sophisticated form of loop for. But if you understand the while loop, in fact, you can do everything with the while loop that you can do with the for loop. It just requires a little more, a few more statements. So the integer repeat is going to be a repetition. Now, here's where we're asking how much I love you. That can be changed. You can try to write your own version of this. Here's our input. Of course, idiomatically, we have to ask for the address of repeat, and we're expecting input between 1 and 10. And now we're going to print out I love you very, and here is the actual loop construction. Here is your comparison statement. So repeat, as long as it's greater than 0, will continue. When it's equal to or less than 0, then this will terminate. We check repeat, it was 0, but here we're going to enter something else. Ostensibly, it's going to be between 1 and 10. So for example, if it was 1, 1 is greater than 0, and then we're going to print very, and then we're going to decrement the auto decrement of repeat. This is very common. Something to iterate on, something to either auto decrement or auto increment, and so the loop ultimately would stop, because if we enter a number, whatever, a positive integer, this will ultimately reach 0. If we enter a negative integer or 0, then it will stop immediately, and then we end with print much. Let's execute this program. I already compiled it. It says, how strong is your love? I'm going to put in 10. Voila. I love you very, 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 very much. I think that should be your goal. Let's try one more time. What if I put 0 in there? It just prints it that once, even though it said, how strong is your love? So I didn't really test for this. Indeed, I can use out of range values. I didn't intend to, and then you get an even longer thing. And of course, if I use the value 1, I get 1 very. All right. So try and play with such a program, or write your own version of that program for Valentine's Day, and we'll go on to something more elaborate. Okay, we have been through while loops, and now we're going to go to a slightly more sophisticated looping statement called the for loop. Now, a for loop acts very much like the while, but is more compact. And you can visualize it as enter the loop, do a test. If you get a 0 value, you exit and do a next statement. Otherwise, you execute the looping statement, go back, test, loop, test, until you get the 0 value and exit. Here's a simple example of what the for loop looks like. For parentheses, so this is a keyword, parentheses, I replaced by 1 semicolon, I less than or equal 5 semicolon, I plus plus. So it's an auto increment, close paren. So there are going to be 3 what are expressions sitting inside this parentheses. And then you have the statement you're executing. In this case, we're going to say print count the integer sheep and go to a new line. And that's what's going to be done throughout. And again, it's conceptually simple. Basically, this loop starts where I is 1, and we test, is I yet 5? If I isn't yet 5, we execute this. So the first time through, we're going to say count 1 sheep, and then we're going to at the end, just before we retest, we do this auto increment. So I becomes 2. We would do a new test. We don't go back to the statement. This is only done one time on entry. This is done each time. This is done each time through the loop. So what are we going to see? We're going to see count 1 sheep, count 2 sheep, and the exit condition is when I is 5, when I is greater than 5. So we will go up to count 5 sheep, and then we won't, at I equals 6, we will skip, and then we'll have to do the next statement. Okay, so that was a simple for statement. Now let's look at the general syntax of that for statement. Keyword for expression 1, semicolon, expression 2, semicolon, and then expression 3. And then the statement that's being executed, which frequently is a compound statement, again, or a block, namely some series of statements that are enclosed in braces. E1 is most typically used as an initializer, just like in our simple example. E2 is typically, well, it's always the terminating condition. So if it's going to work and it's going to be over a finite number of times, then this has to terminate. That's where you can make some interesting mistakes and get what's called an infinite loop. So this has to be tested. E3 is typically, again, this is all typical, the typical use is either increment or decrement. So the terminating condition frequently involves mostly an integer expression or variable, and then incrementing that integer or decrementing it leads to a termination condition. And that's how you typically write or use a for statement. The equivalent in the while, so you should be able to do this mapping, is expression 1 gets executed as a statement. Don't forget that was typically your initial statement, like I equals 1, I assigned 1. Then you have while of the expression, so that's why the expression, the test expression for the loop is E2. Then you execute your statement, and then you do what's typically your increment or decrement, E3, inside a compound statement. So you can see why a for statement is simpler. It combines all these elements into that one statement. So something that would be multiple statements becomes syntactically easier to write using the for statement. But either statement can replace the other. Okay, let's do a more detailed example. We're going to assign to a summing variable a sum of 0. We're going to assign to some condition for termination n equals 5. So we could see if we change this, or if we use scanf to get this, we can get a general number here. And then we're going to say for I equal 1, assigned 1, the test is I less than 5. This is less than, not less than or equal. Auto increment I. So we're going to start with 1. We're going to, of course, count up to 5. So this is going to fail at 5. So we don't have to worry about an infinite loop. And then internally, we're going to do a sum. Sum is going to be replaced by sum plus I. And you should know that this can be done as well with plus assign I. Keep that in mind. And then after the loop, this is not under the loop, and we can show that with this non-indentation, so these are at the same level. We'll print our answer at that point. Now, what will you see executing this? What you're going to see is You will wind up with sum equals 10, I equal 5. Internally, as you go through the loop, the first time sum becomes 1, I is 1. Second time sum becomes 3, I is 2. Third time sum becomes 6, I is 3. The fourth time I becomes 10, sum is 4. And then when I turns into 5, it doesn't get it in. That's the test condition. So we would exit, and that's what we print. Okay, so you should practice with this. Maybe take this very loop, write it inside a real program, place print statements, modify it, and try to do something with not just increment, but decrement.